In this video, we're going to look at an example that is asking you if a set of vectors that belongs to the function space f, are they linearly independent? So we've got this set of vectors sine of x and cosine of x, and it's asking us, is it linearly independent in the function space of all functions that inputs a real value and outputs a real value? So with these questions, they're a little bit more difficult to try to understand in terms of like visualizing it, like what does that mean? But it follows the same process. So what we always do to set up trying to figure out if something is linearly independent is we're going to look at the span of those vectors in the set and set it equal to 0. So we'll start off like that. We'll say the span of S equals 0, right? And this span of S, let's call this C1 times the sine of x plus C2 times cosine of x is equal to 0, where C1 and C2 are scalars, right? And reminder, we are looking for C1 and C2. We are trying to determine if C1 and C2, if they have to be equal to 0 for this equation to hold true. If we can find any other values, then that means that they are not linearly independent, right? And you may be able to kind of reason this one out. We're not able to scale sine of x by any value and have it equal to some scalar time cosine of x. So you could already think that this is probably going to be linearly independent. But algebraically, how would we show this? Well, what we can do, we can actually plug in some test values of x, and then we can set up a system of equations to solve for C1 and C2. So let's plug in some critical values of x. So let's plug in x equals 0, right? We know x equals 0 will be a critical point for sine of x and cosine of x. So let's zoom in a little bit here. We know that sine of x at x equals 0 is going to be 0. So we get C1 times 0, and then we have C2 times cosine of 0, which we know is just going to be 1. This equals 0. We are left with C2 equals 0. Okay, we can then try plugging in another critical point, like let's say pi over 2. Right, pi over 2 or 90 degrees. This is also a critical value, except instead of sine of x going to be equal to 0 here, it's going to be equal to 1. So we now have C1 times sine of pi over 2 is going to be equal to 1, plus C2 times, and cosine of pi over 2 is going to be 0 now. And we are left with C1 is equal to 0. So algebraically now we've just shown what we predicted. So since C1 equals C2 equals 0 is the only solution, S is linearly independent in F. Okay, let's move on to a little bit of a trickier one. Okay. We now have the question, okay, is the set T that contains the vectors 1, sine squared of x, and cosine squared of x, are these linearly independent in our function space f? Well, let's set it up the exact same way, right? Let's do, instead of C1, let's do A, B, and C as our constants. So A1 times 1, or sorry, A times 1, plus B times sine squared of x, plus C times cosine squared of x equals 0, where A, B, and C are all constants. Okay, great. What we're going to do, same exact thing, we're going to plug in some test values here. So let's try x equals 0, right? And we're trying to solve for the system of equations, right? We're looking for, do A, B, and C, do these all have to equal 0 for this equation to hold true? Well, when we plug in x equals 0, we're left with A plus, well, sine squared of 0 is just sine of 0 squared, which is 0 squared, so we get b times 0. And then c is going to be c times 1. And we are left with a plus c equals 0. Okay, let's try our other critical point, right? Pi over 2. Okay, we're left with a plus b times, well, now our sine squared x is going to be sine squared of pi over 2, which is just going to be 1, plus now c times 0, right? Because cosine of pi over 2 squared is going to be equal to 0 squared. And now we're left with a plus b equals 0. So we're looking for solutions to a, b, and c, right? 3 unknowns here. We have 2 equations, okay? We cannot solve this, right? We don't have enough information yet. We have 2 linear equations, and we're looking for 3 unknowns, okay? But we can use this to our advantage, right? You can either try plugging in some more values of x, or we can proceed by taking a look at this equation again, by plugging in kind of what we've learned about our a, b, and c from our 2 test points, right? And we can see from, I'll label them equation 1 and equation 2, if a plus c is equal to 0 and a plus b is equal to 0, well, that means that c has to be equal to b, right? We're adding the same value to a, and we're ending up at 0. So that means that from solving 1 and 2, we can see that b is equal to c. Okay? So let's use that to simplify our equation that we have at first. So we now have a times 1 plus b sine squared of x plus, and now we have another b because c is equal to b. And this is times cosine squared of x. And this is all equal to 0. Okay? We can now factor out the b. We get a plus b, and we're left with sine squared of x plus cosine squared of x equals 0. And now we can see that this is actually just the Pythagorean identity, right? Sine squared x plus cos squared x, right? This is going to be equal to 1. So we're left with a plus b equals 0. And now we've actually got another equation, right? We've got 3 equations, right? 3 equations and 3 unknowns, right? We already used equation 1 and 2. So all equation 3 is going to tell us that a has to be equal to negative b, right? And b has to equal c. So that means that there's lots of solutions, right? Is a, b, and c equaling 0? That is not the only solution, right? Our solutions are negative a has to be equal to b, which has to be equal to c, right? So since that there is more than one solution to a, b, and c, right? Remember what we started with here. We started with the span of the vectors in our set equals 0. If a, b, and c are all equal to 0, they are linearly independent, just like we did in the first example. c1 and c2 were both equal to 0. But in our second example, we can see that a, b, and c, they are not all equal to 0. So therefore, t is not linearly independent in F.